Let us start this lecture with a thought process. I would call him as a traitor who, having educated at expense of society, not paying any heeds to the society, Swami Vivekananda. Because I have chosen this thing because of 15th August was a Independence Day. So, and we should contribute for the society and to have a good bond with the society, right. And if you recall that in the last lecture we discussed about basically how to calculate the heat of reaction using the bond energies, and later on we look at thermochemistry law that is known as Lavoisier-Laplace law, and which helps us in basically using the heat of formation in the forward or the reverse directions, right. And now we will be discussing about Hayes law. We state that in a chemical reaction the total amount of heat will be same whether it is taking a single step or it is taking a multiple steps. In other words, it does not depend upon number of steps, whatever the amount of heat being released, right. That means what is indicates? It indicates that it is a path function or a point function. It is independent of number of steps, that means independent of path, right. That means it is a point function, right. So, and this is nothing but your what you call the first law of thermodynamics, and in other words the Hayes law states that the net heat of reaction depends only on the initial and final state. As I told, it is a basically point function. So, let us take an example. We are interested to find out heat of reaction for water gas shift reaction, which is a very familiar reaction which you people will be knowing, that is carbon dioxide is reacting with the hydrogen getting into carbon monoxide and water, right. Of course, here I have given the heat of reaction is 41.16 kilojoule, right. But suppose it is not given, right, we can apply the Hayes law to find out what will be heat of reaction. How we are going to do? Because we will have to see how this reaction is taking place. It can, right, this reaction can be decomposed into various steps can be used to have these reactions, and for which the heat of reaction will be known, right. For example, like if we know that CO2 is converted into C plus O2, then we know the heat of reaction for that, which is happens to be endothermic reaction, and that is heat of reaction for this reaction is 393.51 kilojoule. And the carbon reacting with half moles of oxygen going to the carbon monoxide, for that heat will be liberated, and this is heat of reaction is minus 110.59 kilojoules, and this is known, right. And hydrogen can react with oxygen is going to the water. So, if you look at, if I sum it up all these reaction, because heat of reaction for all these three reaction, if I can say this is reaction 1, this is 2 and this 3, all reactions are known, then what I will do, I will just sum it up, and if you look at this is cancel it out, and these 2 are cancelled with these, nothing but CO2 plus hydrogen going to the product CO and water, and the total if I sum all these 3 together, I will get 41.16 kilojoule, right. Suppose it is not known, unknown, right, then I can find out by these intermediate reactions applying the Hayes law very easily and find out this, right. Are you getting my point? The application of Hayes law. So, and this, as I told, is nothing but basically it comes from the first law of thermodynamics. Okay. Now, we will be using these thermochemistry laws, right, for our calculations of heat of reaction, heat of formations and other things, right. Now, knowing how to handle this thing, our main objective is to find out basically the flame temperature under adiabatic condition, because that will tell us that how much maximum temperature one can get if you are burning certain amount of fuel, right. So, we will be now learning how to calculate that. Of course, you might have studied earlier also this thing, but let me repeat so that you will be recall and then recapitulate it properly so that you can use it. In a combustion process, if no heat is being transferred, right, which is not true, because this is under what you call theoretical condition or a ideal condition where there won't be any heat transfer, right, and then you will attain a temperature which we call it as a adiabatic flame temperature, right. This we call T adiabatic, that is adiabatic temperature. Let us consider that 1 mole of fuel is getting into a burner along with certain amount of air, and it is basically burning it and getting into a product, right. For example, I can say that 1 mole of methane is reacting with 2 moles of air, getting into 1 mole of carbon dioxide and 2 moles of water, and what will be the product? A nitrogen will be there, right, 3.74 into 2 moles of nitrogen, right. And if now I want to find out what will be the temperature at the exit of this burner, right, provided no heat being transferred, that means Q is equal to 0, right. Now, what we will do? We will have to take a control volume, right. Let us say this is our control volume, right, and keep in mind that this is a flow system, right. If it is a flow system, then we will have to also make certain assumptions. What are those assumptions? Steady flow process, then what else? Change in kinetic energy will be 0, change in potential energy will be 0, right. Is there any work done here? The work done also is 0, right. Under these conditions, you can invoke the first law of thermodynamics, okay, and then you will get that, right. Now, if you look at this adiabatic temperature will be depends on what? Suppose you will get some temperature, we will do that little later on, but it will be depend on what? It will depend on the what is the composition of the fuel air, right, or fuel oxidizer, right, and it will be depend on the initial temperature or the initial pressure, right. In this case, suppose it is 1 atmospheric pressure, right, and if the reaction is taking place in this burner, what will happen to the pressure? Will it increase? Certainly no, right, because it is a flow process, right. So, therefore, it will not increase, but if this is not a flow process, but a closed chamber, let us say this is a chamber, right, is a closed chamber, I am reacting with basically fuel plus air, right, no heat is going out, right, this is my system, and starting with initial pressure is 1 atmospheric pressure, right, 1 atmospheric pressure. What will happen to pressure? Pressure will increase, because why? Temperature has increased, and this is a control volume, right. It is not a control volume, it is basically control mass system or a closed system, right, closed system. So, therefore, the pressure will, in this case pressure will not increase. Is that clear or not? Now, from the first law of thermodynamics, for a adiabatic process with no change in kinetic energy, right, no change in potential energy, there is no shaft work, I will get Hp is equal to Hr. Is it true? How I will get this? What is the meaning of Hp is equal to Hr? That means enthalpy of the product is equal to enthalpy of the reactant. How did I get this? Any idea?
The heat rejected means heat evolved or
that means
will be absorbed by the
product. Okay, that is the meaning, but how did I arrive at this expression? That is the question. First law. So that means you will have to write down your first law of thermodynamics, right? What is that? That is dE by dt is equal to m dot I Hi plus Vi square plus Gzi minus m dot E is the exit, you can say He plus Ve square by Gze plus minus shaft work, right. Steady it is 0, shaft work is 0, this potential energy is 0, right, okay, and adiabatic. So, therefore, this is 0. So, therefore, what you will be getting? You will be getting m dot I Hi is equal to m dot E He, and in our example this is your reactant, right. M dot Hi is nothing but Hi is equal to H reactant, right, yes or no, which is basically Ti, it depends upon pressure, is equal to m dot E He is nothing but what? He is nothing but your product, which is adiabatic and pressure, right. Are you getting? It is very simple, right. So, but what is this Hr and Hp? Basically, we are doing enthalpy balance, enthalpy of the reactant, total enthalpy of the reactant is same as the total enthalpy of the product. That is the point we are doing, and then let me erase this portion. Where Hr is basically NiHi, I is the can be like 1 to R. 1 to R means what? Like if it is methane, right, if I am saying this is methane plus oxygen, right, okay, going to the carbon dioxide, water, right, what will be mole Ni for this? For the reactant side, this is reactant means two reactant, one is methane, other is your oxygen, right. So, if I want to write down here Hr, what will be this one? NCH4 H CH4 not, okay, or I will put not, I will not put not. Why? Because this is not only heat of formation, it is, will it be heat of formation? Yes, it will be heat of formation, total heat of formation, right. And then NO2 HO2, and this each heat of formation will be having two components. One is, this is standard heat of formation, and this portion is sensible enthalpy, right. Are you getting? For this example, similarly, I will have to look at the H product. In this case, in this example, what will be Hp? N CO2 H CO2 plus N water and H water. In this case N water will be 2 mole and N carbon dioxide will be 1, is not it? Yes or no? Are you getting? This I can write down 1, this is 1 into HCO2 plus 2 into H water, and each will be having what you call again the heat of standard heat of formation, right. This is standard heat of formation, why standard? Because it is at 298.15 Kelvin, right, T naught, and this naught corresponding to 1 atmospheric pressure, right, and this T naught is 298.15 Kelvin, and this is from this is sensible enthalpy T naught to T adiabatic, and CPI, keep in mind that specific heat is a function of temperature, right. You will have to integrate over the T naught to T adiabatic. That means, and this CPI is, I means particular species, that means Cp you will be dependent on temperature, also the pertaining species, right. So, how we will do that? That is a big problem, like how to calculate that, okay. And now, so if you want to use this, then only you can calculate what it would be the adiabatic temperature. And keep in mind that for the reactant it is T naught to T. It happens to be the reactant at 298 Kelvin, what will happen? This will be 0. This will be 0 for T is equal to 298.15 Kelvin, okay. If initial temperature is that, but if initial temperature is 600 Kelvin, then I cannot make it 0. This sensible enthalpy cannot be 0, it will be some finite value that you will have to calculate. Is that clear? Okay. Now, what is here happening? Of course, this is we have looked at mathematically, but now we will be discussing little bit about physically what is happening. What is happening? Can anybody tell me? Heat being released. If heat being released, right, those heat will be utilized to enhance the temperature of the product to certain values, right, and that we call it as the adiabatic temperature, provided no heat being transferred from system to its surrounding, provided otherwise it will be lower than that, lower than the adiabatic temperature what you will get if there is a heat transfer between system and surrounding, okay. Is that clear? Now, if you look at this is basically enthalpy line for the reactant, enthalpy line for the product with respect to temperature. This is your enthalpy, total enthalpy, right. Now, if you recall that I had made these two parallel lines, do you remember, right, but now it is not parallel, is it looks to be parallel, right. Now, this is basically, if I say this happens to be 298.15, right, this temperature. Of course, it is not possible, the scale is not that, I have just made like that, otherwise it will be far away, right, and if you take a linear scale, okay. Now, if I say this thing, what will be my this point here? This is basically 298.15 Kelvin. What would be this? This is what I will call? No, this is heat of reaction, right, 298. Okay, let me write down 1.5. This amount of heat, because that is corresponding to standard pressure and temperature, right, and this heat will be utilized to bring this product to adiabatic temperature. So, more pictorially if you want to say, that means reactant as 1 atmospheric pressure 298.15 Kelvin, it is going to the product, and this is the heat of reaction, right, 0, right. And then this heat will be utilized to take this product into T adiabatic. This is just to explain you, okay, but in actual situation is it happening? No, and just to explain I am telling you, okay, actually it will be going on. Is that clear? Now suppose this we are doing, right, and this is a system, right, a control volume or an open system we have considered. Now let us say in a chamber we are what do you call reacting. Let us say methane is reacting with oxidizer and getting into carbon dioxide and water. What will be the adiabatic temperature? How will handle? Will it handle this way, or we will have to do something? That is a question I am asking you, please think about it. Now we will take an example, right, to estimate the flame temperature pentane C5H12, right, with a 25% excess air. Both pentane and air enter the burner at 25 degrees Celsius, right. When we are talking about the burner, basically what is that meaning? Meaning is that we will be using an open system. This is a burner, flow is taking place, okay. So therefore an open system is an obvious choice, and assume that complete combustion taking place. That means what? It will be having carbon dioxide and water, and of course it is with air, so therefore nitrogen will be there. It is an inert gas for this example, and then of course 25% excess air there, that means some oxygen will be there at the end of combustion. So as I told that we will take an open system here, right, because it is a burner, control volume. So the same assumption will be doing, change in kinetic energy is equal to 0, change in potential energy 0, heat will be 0, and work done will be 0, right. This dot I am saying because it will be basically per second kind of thing, you can say. And first law of thermodynamics for control volume is nothing but your Hp is equal to Hr, right. Product, total enthalpy of product is equal to total enthalpy of reactant side. And this reaction we can consider, that is basically pentane. 1 mole of pentane is reacting with basically 10 moles of oxygen and nitrogens, and 5 moles of carbon dioxide, 6 moles of water and 2 moles of oxygen and 37.6 nitrogen. So this is balance. Of course you will have to make, I have just written down here, but you will have to balance, right. Now from this you basically know the products, right. Products are known, reactant anyway it has to be given to find out this thing. Now what we will do? We will say that, and keep in mind that it is 25 degrees Celsius, and we will have to find out Hp. Hp, what is your Hp? Hp is nothing but 5 into heat of formation of carbon dioxide into 6 moles of water, heat of formation of water, plus 2 moles of oxygen and 37.6 of heat of formation. And this is, if you look at, coming from the sensible enthalpy, and T adiabatic minus 298 multiplied by the all this Cp of carbon dioxide, water, oxygen and nitrogen and their respective moles, right, for the balance equation, right. This we know. Now in this thing, interestingly, these are all known. You can find out these values from the table, right. Total enthalpy of the reactant is basically summation of heat of formation of all the participating species, right. 1 mole of pentane and 10 moles of basically oxygen and 37 moles of nitrogen, and you will have to substitute these values from the table, right. That means all are known, you will have to just calculate, right. Now question arises, what the Cp value I will be taking, because Cp is a function of temperature, yes or no? Cp is a function of, right, Cp is a function of temperature. What temperature I should take? Because I do not know the adiabatic temperature. If I know the adiabatic temperature there, then I can very happily use that. Okay. Now let us do something, we can do it iteratively, right, okay, because I will guess some values and then I will find out what it would be, okay. If I substitute this Hp is equal to Hr, and then I will find out this is nothing but your heat of reaction, because these all are 28, so that you will get the heat of reaction. This you get from a table, or you know this individual heat of formation of individual species, then you can calculate, right, and that happens to be 3535 kilojoule, right. When you substitute these values from the table or from heat of reaction, you can take from the table, whichever is convenient, that will be 353 kilojoules. And what I will do, I will have to find out, okay, let us say that 298 Kelvin it would be, it may not be, but I am having two interest here to consider 298 Kelvin values, right. Then what I will be getting specific heat values for these various species as 298 Kelvin, these are the values, right, 37.13 for carbon dioxide, water 35.59, oxygen 29.38, nitrogen 29.14. So if I will substitute these values, right, all those years, right, this expression, right, this expression, okay, equation 1 you can say, then I will get a temperature something 2573.34 Kelvin, right. I am assuming this temperature is what? The product temperature, okay, because these are all product. Which one? These are all product, carbon dioxide, water, oxygen, nitrogen at the product, and that is a quite a big values, right. Now I will take another guess, that is 2000 Kelvin, right, it may be, may not be, right, but I will take that. Then I will get, you know, values, substitute these values, because these are the table, and at, oh sorry, this will be 2000 Kelvin, right, and these are different, you can compare with this. CO2 is very high because 37.13 and 60.35, there is a lot of, because it is a triatomic molecule, therefore it is higher, right, and water of course is higher, but not that much, and oxygen and nitrogen there is also little bit higher. You will substitute these values, then what you will do, you will get T adiabatic 2035 Kelvin, right. Now it is very closer, you can do, otherwise you can make a linear interpolation. If it is a, this temperature are nearby, let us say 298 Kelvin and 2000 Kelvin, you cannot do a linear interpolation. If it is, let us say 1800 Kelvin, you have guessed, and 2000, it is a, there is a difference, and one is higher, one is lower, you can do that linear interpolation if it is interval is small, and then you do. Let us say you are not happy with this thing, 2035 Kelvin, you have guessed 2000, right, this is the guess, right, guess value of temperature T adiabatic, right, and then you are not happy, then what will do, you take 2035 again after that and calculate, and then if you are not getting the matching properly, then you take a linear interpolation, calculate easily. So that is one way of doing, okay. This we will stop over, but you think about like the products is are not known, right, and unless you choose the proper specific heat values, then you will land in a temperature which is quite different than that of the adiabatic temperature. So, with this we will stop over, and we will see in the next class about more about how to handle this chemical equilibrium and other things. Okay, thank you.